Chapter 10 deals with G transform. In part 1, I'm going to discuss G transform, region of convergence, and inverse G transform. G transform was already introduced in one of earlier chapters when we discussed discrete time LTI system. With input G to the n applied, we saw output taking that shape, the same input remaining with some system-related function hg, which actually is related to the impulse response h in that way, and that is defined to be the G transform of the impulse response. In general, G transform is defined that way, and if we put G as a complex number with radius r and radius angle omega, e to the j omega, then we get this expression. And if we put r together with xn, we get that expression, which is nothing but Fourier transform of that signal. So what we observe is that G transform is Fourier transform with xn suppressed by r to the nth power minus nth power. And conversely, Fourier transform is a special case of G transform with radius r. What it says is that G transform is determined for all complex value of G on the G plane, and Fourier transform is a special case of that, determined on that unit circle. Here we briefly consider the relation between the Laplace transform and G transform, or the coordinate, rectangular coordinate used for Laplace transform and polar coordinate applied for this G transform. In the case of Laplace transform, we use the rectangular coordinate, and this one is closely related with the polar coordinate in this way. This radius axis is related to the real axis, and this unit circle is related with imaginary axis, or sigma j omega. Actually, these two are related by so-called bilinear transformation. So this crossing point corresponds to that crossing point, and as a point moves to the infinity and moves to the infinity, and as it goes to infinity, it goes to 2 pi. Okay, goes to pi. So all the properties of G transform, especially regional convergence that we discussed for Laplace transform, this left half plane corresponds to inside the circle, unit circle, and the right hand sided plane corresponds to outside the unit circle. Okay? If you think about this relation, the properties we are going to discuss about G transform, you can understand immediately. One example, we had a similar example for Laplace transform. In this case, for discrete time signal an un and minus an u minus n minus 1. By definition of G transform, we have this and that one. And we know that this one will converge if the magnitude of AG inverse is less than 1. Or this one. And that is a set region of convergence. What's the meaning? The radius of G is larger than the pole, the magnitude of a pole. If pole is located there, that is outside the circle determined by that pole. In this case, we repeat the same thing, and by definition, we have this one, but because of this one, which outreaches from -1 to -infinity, we have this. And we put negative sign to n. Then we can get this expression, and it starts from 0 to infinity if we add 0 point there. So the result is like this, the same thing as that one we saw up there, but the region of convergence changes that way, because this one will converge only for the values A inverse G, the magnitude of that is less than 1. So we have same result, but the region of convergence is inside the circle determined by the pole. Okay? This is right-sided, and the outer part of the region determined by the pole, and left-sided inside the circle determined by the pole. Okay? Another example, we have two right-sided sequences, and by putting them to the definition of G transform, it is easy to get that expression which results in those two poles. This one, the pole determined by that one is this, because it is right-sided, region of convergence is outside, and that one, another pole, the region of convergence, the outer part of that, and the overall function will yield the region of convergence, the common part of those two. Another example, if we have a sinusoidal function like this, with that, by Euler's relation, we get that relation having two poles, one appearing here, another one there. Complex conjugate of radius a third, complex conjugate. And the region of convergence of this right-sided sequence is outward of the circle determined by those two poles of radius a third. Okay? Okay, then now we consider the properties of G transform. Most of them we already know of. First one, region of convergence consists of a ring and the G-plane centered about the region, because it was either this one or that one, which is a circle. Region of convergence does not contain any pole, because if it contains any pole, it will diverge. If Xn is of finite duration, then region of convergence may be entire region, possibly except for 0 or infinity. Because this summation is finite, it converges, but in some special cases it can diverge. You see this example. Suppose we have delta n, whose G transform is 1. The region of convergence is the entire region, the G-plane. But in that case, whose G transform is G to the minus 1, then at the origin it diverges. It has a pole. So, except for that one, entire region except for that point. And the other way, this one with G transform G, entire region except for infinity. If we combine them, suppose we have this xg, then it will be entire region except for 0. And entire region except for 0 and infinity. And except for entire region except for infinity. The next one, finite length sequence. By definition, we get this one, or we may write it that way. And we know there are n poles, n zeros. And n zeros are located on the circle of radius a, like this. There are n, including one there, n zeros. And we have n poles. Among them, n minus 1 poles are appearing on the origin, and the one at the point G is A. There is pole. So the pole of this one is cancelled by the 0 there. So all the poles we have are located there. So region of convergence is the entire region except for the origin. Okay, the next property, if xn is right-sided sequence, and if a circle of radius r0 is inside a region of convergence, then all the finite values of g whose magnitude is larger than r0 is also inside region of convergence. What it says is that if it is right-sided sequence, region of convergence is outside some ring. So if a point is of radius r, then any point outside that one is inside the unit circle. Okay, that is true. And conversely, if it is left-sided, then any point inside a unit circle or inside the pole a region of convergence is there. And so, of course, if a point is inside the unit circle, any point whose radius is less than that one is inside the unit circle, inside the region of convergence. In case of two-sided, if the circle is inside the ROC, then it will consist of a ring determined by the poles and including that point. So, if two-sided, then the common area will be a ring. For the right-hand side, we will have region of convergence going outward. For the left-sided sequence, going inward. So if a point r0 of radius r0 was there, and the region of convergence will be a ring containing that one. Okay, G transform is a rational function in that case. Then region of convergence is bounded by poles or extends to infinity. Yeah, we we know that all those are confined by poles, either outside that pole, in inner part of that pole, or the ring determined by the poles. An example, this one is two-sided because it has two components like that, and we already saw that this one gives you this and that one gives you that. The same thing with the different regional convergence like this. We have two-sided sequence assuming b is less than 1 and 1 over b is larger than 1 and b is less than 1. So outward, inward region of convergence is a ring. A ring. But if b is larger than 1, b, that point is outside unit circle, and 1 over b is inside. So there is no common region of convergence. If xg is rational and right-sided, the region of convergence is the outermost pole. That is, outside the circle of radius equal to the largest magnitude of the pole of the xg. We know that. We already discussed this one. If there are many poles, then if in the case of the right-sided sequence, the region of convergence is outside the ring determined by the outermost pole. And if xn is kosher, that means right-sided starting with n is 0, with all the values are 0 for n less than 0. In that case, the region of convergence also includes g as infinity. It's outside, going to infinity. If it is rational and left-sided, and the region of convergence is inside the innermost non-zero pole, inward, possibly including 0. This one is going to the other direction. The other direction, innermost pole and inside of that one. If it is anti-kosher, non-kosher, left-sided sequence, all values 0 for n larger than 0, then region of convergence includes g is 0. Okay. Another example, you saw this one. This one has two poles, like this. And if region of convergence is outward, it will be like this. Because the common, the part of that one is that, which means region of convergence is outside the outermost the pole. And if region of convergence is ring, it is inside. And the region of convergence is this one. It is inside of the innermost pole. And which of the sequence is two-sided, you know which one is. And we are going to come back with this example later on. If we consider inverse G transform, by definition, we already saw this relation. And if we take inverse transform of that one, defined to be that, we get xn to be that. It means we are taking integration over from 0 to 2 pi on a ring with the radius r. If we replace r e to the j omega with g, with dg being that one, or j omega being dg over jg, then we get this expression. And according to mathematics, it is called a residue theorem, or residue expressed like this. That's a formal way of determining inverse transform. But in practice, there are many other ways to determine inverse transform. For example, table lookup, partial fraction expansion, or direct division, or others. In the case of partial fraction expansion, we get that first, and then take inverse transform of each individual term. For example, in that case, we can do it by lookup table. We know that. But we can try direct division like this, dividing 1 by that, and eventually getting this. And in that case, going inward, we can change the order of the equation and then divide it again to get that type of expression. From that, we can determine this right-sided sequence. And from that, we can determine this left-sided sequence. Another method, we can take inverse transform by Taylor series expansion too. For some complicated signals like that, we take advantage of Taylor series, which is readily known. Like that. The same expression there. Then we get this expression. And from that we can determine xn to be this one for n larger than or equal to 1 and 0 otherwise. In one equation, un minus 1 and that one. We are putting un minus 1 because it is 0 at un is 1. Okay? The next, by partial fraction, we revisit the problem we saw before. And by taking partial fraction expansion, we get this. And when a region of convergence is larger than 2, we know that it should be right-sided. So we get 2 right-sided sequence. In case the region of convergence is a ring, we know that it is composed of 1 right-sided, 1 left-sided sequence, and 1 causal, the other one non-causal, right-sided, left-sided. And third case, region of convergence is the inner part of the smallest pole, the innermost pole. Then we know both sequences are left-sided or non-causal. So we have that. Okay? This is the end of part 1.